Good morning, everyone. Yes, what we were discussing was about systems and everything. Today, we are going to discuss that what is actually doing inside this brain, which we call CPU or any processing unit. What is doing the processing, right? Inside the brain, what is doing the processing? Inside a CPU, what is doing the processing? So that so we are not going to talk about brain as of now, but we are going to talk about first that what is inside this processing unit, which we have in our laptops, in AI system, or in my mobile, or whatever it is, right? And that is called something called transistor, right? Which is the backbone of all these processing, right? And it does processing in very different ways, right? And that is what we know as processing. So with the advent of this digital, which we were talking about, analog versus digital, if we see typically these CPUs and everything, we are now doing processing in digital format, right? So the processing which you are doing is in digital, right? In the CPUs and GPUs and everything. So then what is the processing there? Obviously, one of the example which we gave was if I want to sum two, or let's say I want to multiply two inputs, which is your A and B, right? Which could be 0 and 1. Similarly, this could be 0 and 1, right? And then when you multiply, which is through something called NAND gate, right? Which would give you a, if it is 1, when A and B both are 1, right? So that is one way of processing, right? But what is inside the AND gate? Because still, this is a logical quantity. But when we say logical, that means it is somewhere which is intangible, right? It's a logical means it's something like algorithm. I tell you, okay, that uh, let's say some logical thing which we are saying, right? Let's say, for example, institute, right? Institute is a logical idea. But when you say which institute and then you define, then you are thinking of the building of the institute and everything, then it becomes physical quantity. So to go from this logical quantity to physical quantity is when you need, and this would be mapped to something called our transistors, right? And this is typically taught as when we teach these things, which is a very, very nice book which is written on this, CMOS digital design, right? So this is the exactly what they talk about in this book is how to map these logical quantities into physical quantities and what are the limitations which you get as physical, which we are not going to talk about in this particular video. We are going to talk about our transistor, and the transistor which we are choosing to talk about is called MOSFET, right? MOSFET means it's a metal oxide semiconductor and field effect transistor. So that MOS comes from the structure of how the structure of this is made. And the FET is the operation, right? That how does it operate? And this operates through field. So that is why it is a field effect transistor. Structure, because it's a metal oxide semiconductor. So where you are applying the gate voltage, typically it's metal. Between these two things, it is, and where the things are happening or the current is flowing is your semiconductor, right? And typically it has 3 terminals or 4 terminals, right? Including the body. But we are going to talk about the mainly 3 terminals. So gate, source, and drain, right? Or gate, drain, source, whatever way you draw it, right? These are typically interchangeable because it's a symmetric device. As of now, we are not going to talk about device. We are only going to talk about what is this guy doing that it is able to process, right? And so the beauty is it can find operation in many different ways, right? So let's divide some of the ways. So one thing is the transistor can work as a switch. What does it mean? So for example, when I am designing a NOT gate, for example, here, NOT gate means I'm giving A and I'm getting a bar, which is, that means you're getting 0, right? You're getting 1. So that is also a processing because it's a NOT gate. It's a NOT operation, right? Which is a logical operation, but I have to map it into a switch. So let's just see that what does this transistor, how can I even make this kind of functionality with the transistor, a single transistor, right? So before that, I need to know a little bit about transistor. What does it do? So what I know from the transistor is that if there is a voltage, finite voltage across this VDS, which is the drain to source voltage, and there is this is the VGS. And what we know is if VDS is, let's say, finite, some voltage is there, then what does VGS do? So if VGS is less than threshold voltage or very small, right, or zero, right, we know that there is no current. So this is another quantity, IDS, which is the current flowing through. Let me just make it a little big so that you understand. So what is happening is, this is VDS, and there is a current passing through this, which is your IDS, right? So what is happening is, in this switch is that when I apply a certain voltage that which is very close to zero or less than VTH. VTH is, think of it as a threshold, right? So the very nice analogy which we give is of a tap, right? So you have all seen a tap, right? And you have seen in the tap that there is a handle, right, which you are having in the tap. Okay. So when this is closed, the tap is closed, there is no water passing from it, right? And that is the same case which we see here, that VGS 0 means there is no electric field applied at the gate, or there is no, it's basically the switch or the switch is closed, right? And then this IDS is very close to 0, right? That is what we understand, that is what is going to happen to this, and that is what happens when you've designed a MOS. What happens when I increase this? So that means similar to when I apply certain force, obviously it does not start giving IDS, which I want just now, because I have to apply certain force more than a threshold voltage, right? Then I see a IDS, which is appreciable IDS, right? Finite IDS. Okay. So that is the kind of thing which you see, that if it is closed, this drop, which is 0 here, right? And when it is open, then you see that there is a current. But this is happening after this threshold. So that is the minimum force you need to apply to this to open the tap, right? That is the thing. So then now we understand, okay, the transistor basically is a switch which has a terminal, okay, some input terminal, which is like a tap handle. And then when I am rotating that handle or the tap handle, right, let's say control knob of the tap, which is the control knob of the tap, when I move it after certain force, I start seeing the water flow. Very good. Okay, you have designed a very good switch if you have designed so. So that means now what is going to happen in this, that I am going to see that this is happening. So let's say I will first ground one of the terminals so that I could directly apply whatever input I want to apply here, right? So 1 and 0, I think you know what is the 1 and 0. 1 and 0 is basically a certain voltage mapped to it, right? So let's move. So 0, we could map 0 volt. 1, we could map, let's say, 5 volt, right? It's up to us what voltage, and that is what with each technology may change. But let's say as of now, we are defining 0 volt and 5 volt. So what happens now, because we want to see it as a switch, right? And so we know that when we apply 0 volt here, what is going to happen if there is a finite voltage here? There's no current flowing, right? There's no current flowing. But what is the output I need is 5 volt. So how do I get 5 volt here? Right? That is the question. Because there is no current flowing at 0 volt, IDS is 0. So that means I want 5 volt here. So that is where I use a resistor and a 5 volt supply here. Why did I use? Because when there is no current passing, at the output which I am going to see is basically 5 volt. So this is my 0, which I applied, and I got 1. Good. Very nice. You have designed a very nice NOT gate. Let's check the other functionality. When I apply a 5 volt, what happens when you apply a 5 volt, which is a logical one? So when you apply a 5 volt, given that this 5 volt is more than the threshold voltage, so that means obviously you have to design a threshold voltage which is lesser than 5 volts. So let's say we design, for example, threshold to be 1. So when I design this to be 1, what is going to happen? IDS flows, right? That means current flows. IDS is finite. When IDS is finite, that means there is a drop because this current is flowing through this resistor, and then this output would be very close to 0, right? Because if there is a large current flowing, then this output would be 5 volt minus IR, or the drop across the resistor, which if the current is very large is going to be large, and then this 5 volt will be reduced to 0 volt at the output, which is 0, logical 0. Great. So with this circuit, a small circuit with a transistor, you have designed a switch. Congratulations. That means now I understand. This is the workhorse of, or let's say a simple NOT gate may look like just this, right? But that is not the case in the transistors which we are having, right? Because we found that there is, so this is my NMOS, right? And this is 0, it's giving you 1 at the output. Logical 1, right? But there are multiple things that I would need to know that why this is, but this is the simplest way I could understand a switch. But in the current technology, if I see a NOT gate implementation, it may look something like this. And that we will talk in some other video where we talk about CMOS circuits, right? This is called CMOS inverter. And this we'll talk about in another video. For now, let's focus on the transistor. So transistor as a switch, good. You have used the transistor as a switch, right? Is that enough for our processors? Yes, for the processor, if I'm doing the computing and I'm designing things functionality, I could design with transistors, right? So these logical functionalities, right? Which is we call logical operations. And I think you know all logical operations, which are your AND or NOT, whatever you are doing, multiplication of the digital bits, you are doing addition of the digital bit, or you're doing whatever other operations, right? You're doing. So this is different from arithmetic operation. Arithmetic operation could be subtraction and all that. Logical operation are defined in terms of gates, right? So that is what we know of. So then logical operation, then transistor as a switch is going to power all of that. And one of the example we saw was the NOT gate. Okay, so that opens you to understand, oh, wow, this is the workhorse of the current CPUs, GPUs, or whatever processing unit I talk about. And there are billions of these transistors together working to make a particular functionality or task is what is making all the computing possible. Okay, with that, I would end this video and see you in the next video. Thank you.